All right, let's dive in. In this explainer, we're going to architect a modern AI data pipeline from the ground up. We're going to cover the entire process, starting with just raw text, all the way to a production-ready retrieval system that can power some seriously sophisticated AI applications. By the time we're done, you'll have a really solid architectural understanding of how these core systems actually work.
This one really hits home for a lot of us, right? You've probably felt this. Your AI app feels slow, it's giving weird answers, or it just feels dumb. And your first instinct is to blame the LLM. But here's the thing, 99% of the time, it's not the model. The real problem, the true bottleneck, is almost always how you're finding and feeding it the right information. And that's exactly the problem we're here to solve.
So here's our game plan for today. We'll kick things off by really defining the retrieval problem. Then we'll get into what vector search actually is. The main event, though, is the 5-stage pipeline. That's our architectural blueprint. After we've built that, we'll see how it powers modern AI through RAG, and finally, we'll talk about what it really takes to make these things production ready.
All right, first things first, vector search. What is all the hype about? Why is this such a game changer? Well, at its core, it's a huge shift in thinking. We're moving away from the old world of just matching exact keywords and into a new world of understanding actual concepts and meaning. It's way less brittle and a whole lot smarter.
The secret sauce that makes all this possible? It's a concept called an embedding. And really, all an embedding is a long list of numbers, a vector. But it's a very special list of numbers that somehow manages to capture the meaning of a piece of text. You can think of it like a mathematical fingerprint for a concept. This is the exact point where abstract language literally becomes math.
And this right here shows you exactly why that matters in the real world. Look at keyword search. A user types trouble logging in, but your help document is titled Reset My Password. Keyword search comes up with nothing. It fails. Why? Because the words don't match. But a semantic search system, it understands that the intent behind both phrases is the same, and bam, you get a match. This isn't a small tweak, it's a massive leap in capability.
Okay, so now that we get the what, let's talk about the how. This is the core of our whole session today, the 5-stage pipeline. I want you to think of this as the architectural blueprint for pretty much any serious vector search system out there. Doesn't matter what tools you use, these fundamental stages are always the same.
And here they are, the 5 pillars: ingestion, chunking, embedding, indexing, and finally, retrieval. Seems simple on the surface, but getting each one of these right is absolutely critical. You mess one of them up and the whole system starts to fall apart. So let's break them down one by one.
First up, data ingestion. Now I know this sounds like the boring part, but trust me, it is foundational. That old saying, garbage in, garbage out, is like 10 times more true here. The quality of your final search results can never be better than the quality of the text you put in at this very first step. Your vector DB will happily ingest messy data, but your users, they're going to notice.
So what does good ingestion look like? You have to be deliberate. First, strip out all the junk, the website headers, the footers, the nav bars. That's just noise. But you also want to preserve meaningful structure, like H1 and H2 tags. And this last one is so important. Keep that rich metadata, the source URL, the author, the creation date. You're absolutely going to want to filter on that stuff later on. It's incredibly powerful.
All right, stage 2, chunking. And let me be really clear about this. This is where most retrieval systems fall apart. It is the silent killer of performance. All we're doing is breaking our big documents into smaller, more manageable pieces for embedding. Sounds simple, right? It's not. Getting this right is part art, part science, and it has a massive, massive impact on your results.
And this slide just nails the core dilemma. It's a balancing act. If your chunks are too small, you rip a sentence completely out of its surrounding context and the meaning gets lost. But if your chunks are too large, you dilute the core idea with a bunch of other noise, making it really hard to find a sharp, precise match. Finding that sweet spot is absolutely key.
Okay, on to stage 3, embedding generation. This is where we take each one of those text chunks and feed it into a specialized model. That model then spits out our vector, that mathematical fingerprint of meaning. Now there is one single golden rule at this stage. You have to use the exact same model to create your stored embeddings as you do to embed the user's query at search time. If you mix and match, the whole system will completely break.
The good news is you've got plenty of options here. You can go with the big commercial APIs from places like OpenAI and Cohere. They're powerful and super easy to use.
Or if you need more control or you're concerned about privacy, you can run your own open source models, like from the Sentence Transformers library. The choice really just comes down to your budget, performance requirements, and how much control you need.
So, you've got millions of these vectors. Now what? You can't just scan through them one by one every time someone searches. That's where vector databases and indexing algorithms come in. And here's a key concept for any real-world system. We almost always trade a tiny bit of accuracy for a huge gain in speed. We're looking for approximate nearest neighbors, not perfect ones. And for user-facing applications, that's a fantastic trade to make.
This table kind of breaks down the main options. On one extreme, you have a flat index. This is brute force. It literally compares your query to every single vector. Yeah, it's 100% accurate, but it's painfully slow and just doesn't scale. On the complete other end, you have something like HNSW. It's blazing fast, it's what most production systems use, but it uses more memory and it's an approximation. Your choice of index is a critical engineering decision based on these trade-offs.
And at last, stage 5, retrieval. This is the payoff. A user submits a query. We take that text, run it through the exact same embedding model to get a query vector. Then we send that vector to our database, and the index does its magic, instantly finding the top K, the top 5 or top 10 most similar document chunks from the millions we've stored. Those results are what gets sent back to our application.
So we've designed this powerful retrieval pipeline. But what do we actually do with it? Well, that brings us to Retrieval Augmented Generation, or RAG. This isn't just a buzzword, it is the architecture that powers the vast majority of modern, data-aware AI systems today.
And the flow is actually pretty simple. 1, a user asks a question. 2, our pipeline does its thing and retrieves the most relevant text chunks. 3, and this is the key part, we don't just show those chunks to the user. We inject them directly into a prompt for a large language model. We're essentially telling the model, hey, using only this information I've just given you, answer the user's question.
And this is the most important takeaway for RAG. An LLM knows a lot about the public internet, but it knows absolutely nothing about your company's private documents. Its ability to give a smart, relevant, and accurate answer is 100% dependent on the quality of the context you provide it. The retrieval system we just designed is quite literally the foundation for the AI's intelligence.
Building a prototype is one thing. Deploying a robust, scalable system that real users depend on, well, that's a whole other beast. So for this final section, let's put on our infrastructure hats and talk about the engineering challenges of making a pipeline truly production-ready. This isn't just a list of nice-to-haves. This is the stuff that will keep you up at night. What happens when your documents get updated? You need a re-embedding strategy. How fast does the search need to be? You have to meet strict latency budgets. How do you handle thousands of users asking the same question? You better have a caching layer. And security? Access control is absolutely non-negotiable.
Here's the bottom line. A vector database is not just another library you import into your application. It is a core piece of your data infrastructure. You have to design it, deploy it, and maintain it with the same rigor and seriousness as you would your primary production database.
And that brings us to the final thought I want to leave you with. You've followed the blueprint, you've built your pipeline, it works. But what happens when your data grows from thousands of documents to millions? What happens when your user base goes from 10 people to 10,000? Is the architecture you designed on day one truly ready for that kind of scale? That's the question every senior developer needs to be asking.